on Thursdays. Homework 7 and 8 are released, and that's it for homework. Just 2 more homework assignments. And you guys can just dump all that. Well, then there's a midterm, second midterm, and then you just dump all the material. Perfect. Any logistics questions? Yeah. It's due during break. Is that the 14th is the break?
Yeah.
Okay, fine. Let's see. You want to deal with facts and like logic? No lecture. I'll just make it due at the, I'll adjust the dates so they're not due during break, but they're due later. So, yeah.
Thank you.
And then I'll adjust the other one so that's a little bit later too.
Because that was the week.
I got the worst out of the way. It's the first year.
Good logistics question. What else you got? See, at least somebody's reading the website, paying attention. That's fantastic. Okay, great. So last lecture we talked about serial buses in general, or just bus structures in general, some of the pros and cons. Then we're going to look at 3 different individual bus structures and protocols. So we talked about UART last time. Now we're going to talk about SPI, and the second half of class will be on I2C. For reading, you get excited. The reference manual is great. There's lots of references online. Maybe that's where you would want to start anyways. But if you want to look at the textbook, it's chapter 22. Okay. SPI is a very common serial protocol standard. It allows for bidirectional communication. It's synchronized, meaning that it has a clock, and it's really designed for chip-to-chip communication. While UART was actually designed for computer to computer, and then we repurposed it, this was designed from the ground up for chip-to-chip communication. It's fully duplex, meaning that you can transmit and receive at the same time. UART was as well, and while that isn't necessarily the modality that you always use it in, it has a separate bus, so this one wire. So this is, I don't know, controller data out, or SPI data out, and this is SPI data in from the controller's point of view. So there's a line for data out, line for data in. There's a clock, and the new piece here is the chip select, and that's used for arbitration, because you have to be able to tell which chip of all the chips that are on this bus should be talking. So that's the arbitration part, and this is generally pretty fast. So we can get up to megabits per second. One of the challenges, as you'll see for SPI, is there's not a IEEE standard for this. This is kind of like a methodology for communication that's kind of evolved over time, and things like clock polarity, bit polarity, timing, all those things have generally just been agreed on by manufacturers, and now it's kind of coalescing into a set, a more well-defined spec, but it's not governed by anything. At least that's not how it started out. So this would be an example of how to do wiring for multiple devices. So here we have one controller. Your controller in this case is your microcontroller. It's the thing that's going to be in charge of handling communication. So here's a controller. You have different numbers of peripherals, and they share, to reduce the number of wires, they reshare some bus structures. So everything uses the same data out, the same data in, the same clock, but they all have unique chip selects. So your microcontroller will say, I want to talk to specifically, say, peripheral 2, and it'll raise that line. Then peripheral 2 will respond to, will accept data in or transmit data out when asked. So it's, in some ways, it's not necessarily just a 4-wire interface, because it's n number of chip selects, 1 chip select for every device you have on there, plus ground. So typically controllers select peripheral with a low. It generates the clock. It shifts data out. So you're going to use this data shift register idea again. You're going to put data in parallel, and you're going to shift data out to the receiver, whatever that object is. Any questions so far? I do like monologuing, but it might not be the best for learning. Yeah.
There's a different name for serial data out. So, isn't it called like MISO? Like
Well, yes. We'll get to that in a second. We'll get to there. Yeah, sure. Let's talk about that. So the traditional, not traditional, maybe traditional, is master and slave. That was the terminology that was used since the 50s and 60s and 70s, right? And so do I think our forefathers were like, aha, I'm going to encode racism into our specifications? No, I think my grandfather and your fathers were just like, I'm in Silicon Valley, I'm just going to make a thing, and weren't thinking about the consequences. And then people have become more enlightened about this and made different choices. And so now there's a move in Silicon Valley to go and rename these things. And you can decide whether that's a good thing or not. I would just point out that you, in a few years, will be in the position to name the naming conventions for your bus structures. Whenever you're going to make a peripheral, you get to name it. And that puts the responsibility, or at least the opportunity, back in your hands to choose bus structures that will be more inclusive. So it's up to you what you want to name these things. But since there is no spec for SPI, you'll still find documentation that names it both ways. So it's up to you to understand. In this class, we'll just use SDO, so serial data out, serial data in, and most companies have gone and switched their naming conventions. Any other questions? Okay. So the most primitive way to think about SPI controllers is that just a bunch of shift registers linked together. And so what will happen is you will say, okay, go, and then you'll sequentially clock data. Let's say, what would this be? Clock data, say, out of here, and then that will sequentially clock data back in. So that's way is, in this consensus, is fully duplex. So you have data in one, data in the other one, and they're just going to transpose each other. It's going to go from one device to the other device. Typically, that's not necessarily how it happens, although this is what the underlying structures look like. Usually it's the controller says, I want to send you data, and it sends data. This may not have any data to send back. So we'll just put all zeros in there. You won't see any data on the serial data out line or in line. Okay. Packet size can vary. It could be 4 bits. It could be 16 bits. Typically, it's 8 bits. Anybody know why 8 bits is a happy number? Specifically for serial protocols. Yeah.
It's a byte.
That's true. That makes me happy. Any other reasons why it's a happy number? Yeah.
Because it's a byte, it's in exactly one address.
Maybe. I was more thinking about ASCII. So oftentimes we use ASCII, and that's what a lot of these protocols are here to push back and forth. So ASCII is just a method for encoding binary or alphanumeric information in binary. And so you might find for your projects that you like human readable things. You might not be so good at on-the-fly binary conversion in your head. It's fine. Neither am I. And so you could go and have 2 devices just talking back ASCII. ASCII is probably more relevant when you're talking about UART, because you're going to be sending stuff for your controller, probably up through your USB cable up to your serial terminal. Yeah.
The max ASCII value 255.
There's ASCII and there's like extensions to ASCII, but I think, I don't know, you've gotten to the limit of my understanding now.
Wouldn't that be the 28 bits?
Yeah. But yeah, so there's like, in ASCII, there's like capitals, lowercase, numbers, special symbols, special characters like character return and next line and those sort of things. And I think maybe that they've extended that in Unicode up to larger and larger numbers or values. Okay. There's no flow control or acknowledgement in this protocol. There was, in early versions of UART, there was lines that would be raised and lowered if the data was received, if it was ready to receive. That's not going to happen in this protocol. One of the challenges here is the peripheral has no method for telling the controller, I have information for you. Right? So Say you have a sensor, common one would be a sensor like an accelerometer, and your device is in free fall. So like the first iPods, what they would do is they had discs in them. So they would take, when they noticed they were in free fall, they would take the head off the disc. So when it landed, they wouldn't damage the disc, right? So there's a common idea. The problem here is your peripheral has to somehow tell the controller, move the arm out of the way because you're in free fall, you're gonna hit the ground. So what's one methodology for getting around that? Oh, you weren't raising a hand. Okay, that's too bad. What could we change? Yeah, you could, where would you put the interrupt?
Somewhere else.
Somewhere else. Good point. You can go and add extra lines, and a lot of times you'll see chips that have extra pins that are specifically for communication. Those have external interrupt, and then you can configure it here to raise or lower under certain conditions, and you have to run that back to the SPI controller and through another pin. And so now you have these, this all about communication, but it's not part of the protocol, so I had to add extra things into it. All right, so let's look at a false add example. You know how I love false add. All right, so in this complicated design, why does it look like that? Because, okay. You can't read every word here, I bet, way back there. But I put notes on this time so I could remember how the thing works. So we're in luck. Here, this little thing is going to be a sequencer, and all that means is this a bunch of Boolean logic in there that will put out 8 pulses and then take a pause, and put out 8 pulses and put a pause. So it's just taking the clock and making clock traffic. In fact, we can just see that right now. Yeah. And here, no data is going out now, and just activated the clock here. So here it puts out 8 pulses and then takes a break. Yeah, I was even right. Great. And then, so here we have our SPI controller. We have parallel data in. We can load that parallel data with this load button. To make this simulation work, you want to have one SPI clock cycle go first. Of course, that's not how it really is, but in false add, it just makes life a lot easier. And then we have peripherals here. So we have a serial peripheral 1 and serial peripheral 2. We'll go and select one of those. So here's the select pin. And now I will go and load this out. So on the next clock cycles, we can see here is the data coming out on SDO. And it is, let's see, low, high, low, high, 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 low, high, low, high. And stop. Oh, stopped. Stop. You can see the tail end of that data was being transitioned into this register down here. I'll play it again. I didn't add any logic here to stop after 8 transitions. It's just going to keep clocking it in with the clock. But you will see here that that data is making it its way there. So let's try that again. All right. And I'll speed it up a little bit. Data, 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 data. And you can see this data is getting shifted in here. See, this is starting to mirror what's up there. And yeah, if I stop it here, you can see, yeah, I think that's exactly right. So it was, up here was 1, 0, or 0, 1, 0, 1, 1, 0, blah, blah, blah. And you can see that's been shifted in to that register down here. And now this device is ready to pull that data out and do something with it. Any questions? Yeah.
Is it taking like D7 first, or is it taking D0 first?
You and your device have to figure that out. There's no set protocol of whether it's supposed to be most significant bit or least significant bit first. So you'll find with a lot of these bus protocols is that they're so primitive. I mean, like you're looking at waveforms that you actually have to a priori discuss with the receiver and transmitter what's the format of that data. Is it going to be 8 bits? Is it going to be most significant first, least significant first? all those sorts of things. It's different than, say, USB, or USB 3, which is a much more complicated protocol, and all that's already predefined. But it's less flexible in that sense. What other questions do you have? No, this is perfectly clear? No, I didn't even get the right response. Nobody shook their head. They're all like, it's Monday. I don't want to talk to you. Okay, cool. But I encourage you to play with it. If you do play with it, just make sure you put 8 clock cycles out first. It'll technically still work. It's just the data will look weird for the first time. Okay. So SPI timing diagrams. So this is one way to show them. Here we have a clock. Chip select goes low. Actually, I think I had that wrong in my previous diagram. I forget. I think I actually had it chip select high. It should be chip select low. I had it wrong in Falstad. And then you have your data frames here. So there's a setup and data frames. But SPI gives you, because there's no spec, it gives you lots of different possible ways to control this. And we'll show that in a second. But here in this particular case, you're going to clock data in on the rising edge, let's say. But that's not the only opportunity. So you can have all 4 options. You can have, clock polarity can either be high or low. So you can either start, and they're saying that the clock either starts low or starts high. And then you can have the clock phase, meaning when is the data clocked in, either on the rising edge or the falling edge. So that gives you 4 different clocking in strategies. And this is where the confusion came up early on. I remember when I was at Intel as an intern, making microcontrollers talk to peripherals, and it was like, oh man, that little, I don't even know what it was at this point, probably distance sensor or something, right? Its SPI was only one of these. I think it was like quadrant 1, but my microcontroller only talked 1 and 2. And I was like, oh, I just can't get these 2 things to talk to each other. But now you have lots of different, generally you have lots of different options now because microcontrollers have gotten more advanced. So to kind of think through some of these clocking strategies, this will show it. These are the 4 clocking modalities. So here, clock polarity and clock phase. And they're showing you here the transition would be in the center of the data. It's just showing you where the clock is. So this would be start high, but rising edge versus falling edge. And that's low, low, so rising edge and falling edge. Something to keep track of when you're working out there in the lab and your final projects. So this is just a typical bus transaction. While they are fully synchronous and can talk at the same time, that is usually the non-traditional case. Typically it is your controller is going to send out some command or some value, right? And so here we have an ASCII X, and for whatever reason, when the peripheral is supposed to talk back, it's going to give, it chose to give a clock or ASCII F. In this case, the controller, the programmer here has to know that to send data back, is going to go out and put an extra just clock phase out there. So here went 8 clock pulses. The controller is sending out S, and then part of the specifications for the peripheral, you look in their data sheet, you say, oh, then put out clock and it will return data. So there's no reason why, from this diagram that this is the time when the peripheral would send data. It just happens to be what the bus transaction was doing. And to say it another way, there's nothing about the spec that says this is to tell the peripheral when to talk. It has to be agreed upon as part of the response to an S, was the peripheral would write an F. Here you don't necessarily have to bring the chip select down or back up. You can if you want. Depends on what the peripheral spec is, but you could just keep it low the whole time to indicate that you're going to keep focus on that particular peripheral. Okay. There's no specific data rate. There's practical limitations here, so tens of megabits per second is usually where we're at with the spec, but there's no maximum defined rate. It uses traditional push-pull transmitters and receivers, so CMOS and NMOS and PMOS drivers that are going to push the data out. Here are some standard frequencies that you'll often see manufacturers go for. Ooh, this should be. Okay. We did talk about this one for a little bit already. So this is just an example of, for this particular gyro, that you get interrupts. So it could be interrupt when data is ready. So say you do a conversion, you've told the thing, go take an ADC measurement or a measurement in general. And these things don't often happen. It may need some hold or setup time or some wait time. So it could have a GPIO pin that says, okay, I'll ping you high, I'll go high when this data is ready, or it could be event-based. So oftentimes you'll see multiple interrupt lines that will encode different amounts of information. What was it again? So there's other configurations that you could use this in. So one common one is for lighting control. So you can daisy chain this. In this particular application, you are clocking data into peripheral 1, and then the out of, so data goes into peripheral 1 and the out goes into peripheral 2. Then the out peripheral 2 goes in peripheral 3. And so in this particular case, all the chip selects are always connected to everything. So basically you're shifting data from one device. So if you want to get the data at device 3, you shift it through 1 to 2 to 3. And so that's a way to reduce your wiring complexity because you only actually needed 4 wires for this. 1, 2, 3, 4, even though you have 3 devices. But now instead of having a chip select for your arbitration scheme, you have to take time. It takes extra time to shift all that data through. And your peripherals would have to be configurable for this particular scenario. So LED lights are one common way that uses a version of something that's close to SPI, and these are strip lights that are all individually addressable, and you actually shift all the data to them and then hold on that data, and then it changes, it will change color. So you have to ship fast enough that people can't see. Any questions? Okay. Let's see. Yes, and this is just, this animation is just showing, oh, but it won't stay for whatever reason. Green, green, and it goes away. Cool. Just showing that the data here gets transferred down to that next one for the next device. For your devices, for your device you have in lab, they have 3 SPI modules, each with their own dedicated IRQ line. So you could have multiple SPI peripherals. Why would you need that? Why would that be a good idea, considering that you can already put multiple SPI peripherals on one bus? Why do you need to have 3 buses on one device? Why don't you take 30 seconds, talk to your neighbor, come up with some possible reasons.
SPI module only has one control. You can only read from one master on each bus. Use the master terminal. You just load one device up at a time. Yeah. Maybe you want to.
Faster.
Peripheral, you would need more. It can. It's supposed to. So. Like the controller.
Oh, yeah, never mind. So maybe you have 3 bytes of data, or no, well, no, you're good.
Through all those.
Yeah.
SPI module.
Yeah.
All right, why do you think? Why do we have 3 SPI modules or peripherals on this particular chip when you can talk to multiple devices already with just one module? Yeah.
Yeah, different devices might run out of needs for SPI, so having more options of different signal clocks might be helpful.
Yeah. Okay. Yeah, no, I could see where that, we could find counterexamples too as possible where you're like, oh, well, this chip won't respond, but I haven't selected it. So I'll have one clock speed for one chip, and then when I select a different one, I'll do it to a different clock speed. But that's also complicated and maybe has other unintended consequences. So that works.
Maybe one peripheral wants to use SPI, but you want to access it at the same time as another peripheral. So then having 3 modules lets you access 3 at the same time.
Okay, that's, you're thinking about time as a commodity. That's good. Any other reasons? What about this horrible, overcomplicated slide? Okay, so this one, we have these different clocking polarities. You have 4 different possible modes, and this means that your clock could be positive, negative, clocking in on the rising edge or falling edge, so 4 different modes. And so you imagine that data may be misinterpreted by one peripheral who is expecting one mode versus a different peripheral. So maybe because the data format layer is different between them, maybe you'd want to separate those on different buses. Any other exciting reasons? I like the clock one. I didn't think about that one. All right, so pros and cons. So wiring is relatively straightforward. So 4 wires plus whatever number, well, 3 wires plus n number of peripherals because you have chip select. And that's also, you also need them to be connected with ground. So at least 5 wires. Faster than asynchronous serial, so faster than UART. No addressing. We're going to talk about another scheme where you actually have to have an address. And so arbitration is relatively simple to implement. You have a chip select line. The challenge here is that it's not particularly scalable. So if you get to 100 devices on your embedded system, they all have SPI. Well, that means 100 extra wires for chip select. So that's going to become untenable unless you did something like a daisy chain. But again, daisy chain is only available for devices that has been specifically designed for it because it's not common to use that anymore. There's no acknowledgement capability, so if the device didn't catch the data, you don't know, right? Your microcontroller sending out data out, maybe your peripheral was busy, unavailable, who knows, or maybe it was powered off. You don't get any acknowledgement to know that the thing wasn't there or didn't read the message. And you only have the controller is the only thing that can initiate communication in the context of what SPI is, although you have the alternative methods of adding extra pins for interrupts. All right, so kind of blasted through that. What other questions do you have? You must have questions.
So like, let's say you're trying to use SPI with a temperature sensor.
Yep.
Are you treating the temperature sensor as a singular register that you can read and write that just happens to get filled with the temperature, or do you use like the data write line to say I want to talk to this register inside of the temp sensor? Like
yes.
Like with the APB stuff.
It depends on what the spec is for your peripheral. Okay. So sometimes it may take multiple transactions to set it up. So you might have a whole, like, you would send an address for a register that's inside the peripheral. So imagine this thing has multiple addresses and the registers that say control when the interrupts go off, under what conditions, or how sensitive you want your gyro to be. And so you would probably be address data, address data, address data, address data. And then it would be all filled up or ready to go, and maybe there's an acknowledgement command. But that's not part of this protocol. That's built on top of this protocol. So then you have to go read through your data sheet to figure out what is it you're supposed to be sending.
Gotcha, thank you.
Yep. Yeah.
Are the signals that we learned for like general controlling protocols like are those a specific type of protocol, or is that just a general typological thing?
Those are that's a good question. That is for inside your chip. That's the only place that it is applied. And so that is for the APB bus, so the advanced peripheral bus. So that particular protocol uses those lines. But that protocol doesn't exist from chip to chip communication. It's only for the bus structures internally. So these, in that sense, have a lot fewer lines, right? Because we don't want to have to pay the penalty of having GPIO lines for P-ready and address and all those other things. What other questions you got? You ready to do a lab on this? They're all like, it's Monday. Okay. Well, why don't you guys take a minute just to talk amongst yourself, do anything you want, give you time to wake up a little bit, and we'll go into the next lecture, the last part of serial buses.
The difference between
Take a second to like be. I remember you mentioned you'd be studying a lot over the weekend. Did you have a chance to enjoy the weather outside? Like the clock.
I did. I sat outside and then I immediately lost all of my keys.
you were have
I lost my lanyard with all of my keys.
That's when you're doing every like. That I don't know.
We were on the bus, and when I was at my apartment door, they were no longer in my pockets. Oh no! I just knocked on the door to my roommate. But
That is something that.
it's homework 5, right?
and now I'm just tired.
Yeah, so right here, you are just this horrible.
In the background. Every time he's been like.
I wouldn't go home.
That's the one where it's just like. Yeah.
Talking about how you had some virtual time. We were pretty close. It's just reading all of this stuff. So I was saying that with these phases of the clock, that's independent. You still have a data in or data out dependent. They do look the same, right? The difference is
If I can like find the time to just do it, like the attacks was like send me.
sure. So you toggle, do the falling edge before and this one, rising edge.
Yeah.
So sensors or something.
That's good.
My friend is working on a sensor.
Just like motion.
That'd actually be cool
Distance
if we
or
can
something.
add like a camera to it.
Yeah.
It's like
Modules. Why are there 3 modules? That means there's
already like you need to do something in a limited number of times. You can add interrupts in there or something. I think if we had a camera though, and they would add
not for glass.
some motion tracked elements. So it's like you don't have to hold the device. Maybe it's like some sort of yeah. It's like
All right. So, did your conversations make any new questions about SPI before we go on to I2C?
Block diagram you briefly showed us.
Sure. Now is a great time to do it. All right, so first let's try to understand whatever this is. So this is saying the clock could be in 4 different modes. And one of the modes is that the clock starts high. It's normal. Resting state is high. And so that would be these 2 bottom ones. And then these 2 are when do you clock in data. So you're either clocking in high, or the rising edge, or the falling edge. So it could be that you are in mode 3 here, the clock is normally high, and then when you want to clock in a transition, you have your toggle edge and you sample here. So you're sampling on this particular edge. Okay? And so this is flexible in the sense that it gives you the options of either having high polarity, low polarity, or clocking positive edge or negative edge. How do you feel about that? Your head says this, but your eyes says, I don't know what he's talking about.
Explain sampling versus toggling.
Sure. Probably easiest to do that here. We could say setup phase as well. So here's where you're sampling data. You're clocking in data here. And then here's where you're toggling. You're toggling the state of the bus. Yeah.
Why would you want to change the phase by having it to low?
Why would we even want to have these options?
Like the phase specifically, you either wait for the second edge or you start capturing on the first edge. Why would you?
Well, it's more about you're more consistent through all. It's not that you change it dynamically. It's that you just set up. Like if I inverted the clock, that would be one of those modes. It would still work. Do you agree with that? And then I could also say, well, I want to sample on the falling edge. but I'd have to move the whole clock half a period over because I don't want to actually sample when I'm during transition. So it's just, yeah, go ahead. Okay, so then we'll go over to this complicated diagram. So what's this thing trying to show you? Okay, so here is data, okay? This is when the data is being sampled. This is showing you 4 clocks. Now, this bus doesn't have 4 clocks. This is showing you all the options that there could be. And so you have, let's see, clock polarity 0, so it's normally low, and then you're sampling on the rising edge, so that would be clock phase positive. And so they're just showing you here, I'm going to sample in this. Now, the other one would be, let's see, clock polarity 0 starting, and then you're clocking a negative edge. So they've just artificially moved this clock back a little bit, just for the purpose of this diagram to show you that this is where you would clock in. That makes sense. Otherwise, you could have 1 clock, but then you'd have to have 4, to make the diagram work, you'd have to have 4 data versions underneath. So this is just one way of representing that. But if it doesn't make any sense, that's fine. Just remove the 3 other ones, and then just look to see how it works, and then look at each clock individually, and then you should see how it clocks in. And you're going to be in your data sheet, you're going to be like, I don't understand why it doesn't work. And you just have to, this is something to look out for, because it gives you all the options to hang yourself on. Any other questions? Does that answer your question? I feel like you're looking at me and you're saying, no, it don't make any sense. This guy's crazy. All right. I taught one person one thing today. Feeling good. All right. Yeah?
I guess I'm still a little bit confused on how this relates to the data coming in. So does the data coming in get transferred to the peripheral on those sampling edges or on the toggling edges?
It is independent of whether data is going to the peripheral or coming from the peripheral. It's always being sampled or latched on the sampling edge, and then there's the transition edge, toggle edge, whatever you want to call it, setup phase is the alternate, the alternate transition. Does that answer your question?
Then what is that? Why is setup phase after the data comes in? Oh, I get. Okay. I get it.
You tell me what you got. Tell everybody else what you figured out.
Okay, so the sampling edge is when the data gets latched in.
Yes.
And then whatever the peripheral wants to do with the data, or whatever the microcontroller wants to do with the data, it does during the setup phase. And then it's ready for the next one. And then that next piece of data comes in or goes out on the next sampling edge.
Okay. So if I said, so this is the sampling edge here. I'm going to say this is the toggle or transition edge. Does this still work with your version of what you were thinking? So here, we're just indicating, can you see my cursor? Yeah. That we're going to sample at this edge, and we're going to look here and say, oh, this SDO is high, so it's a logical 1. Then you transition. Well, we didn't want to, in this particular case, it was 1 again, so that gets toggled high, and then you just get sampled in, that rising edge, and then here, the data is going to change, or this is when the setup phase, or the toggle phase is, and here the data is changed. The data needs to stabilize, and then on the rising edge, it gets clocked in.
Yeah.
Okay.
Yeah.
Great. Yeah.
So basically, toggling edge is the edge that tells the peripheral to prepare the next data.
Yeah, you can say that. It's a cool. Yeah.
So you got peripheral. I'm done now. You can change to the next data.
Yeah, I never thought about using that phrase, but yes, exactly what happens.
Okay.
Yeah.
In SPI, do we end up losing any bits of data during the setup phase, like when it gets stabilized, like the data in SDO?
Well, the setup phase is only half a clock cycle. Right, so here we're setting up data. So here we've clocked data in, and now we're going to set up here. There's a transition occurred. And all the chip designers made an agreement that within this particular clock phase that you can get set up within that time frame. So the negative edge falls, the chip says, okay, I'm going to change my data, and then it's instantiated on the bus, meaning it's stable, and then it's sampled in the next rising edge.
So the first 2 full clock SCK cycles are just like we disregard all those data, like those first 1 bits, first 2 1 bits, right?
What do you mean? I'm only, the rising edge is the rising edge. It's gonna clock in data. What do you mean disregard it?
But we haven't stabilized like SDO data coming in, right?
Sure it is. I see this simple diagram shows that to be dark, slightly darker than the other one. Let's just call that stabilized. Let's just say it is. Say another way, the peripheral, right, wants to get that bit, when chip select goes low, right, now you're selected. Now it says, get your data ready. So this is the time between chip select going low and that first transition edge. The peripheral's job is to have the bit on the bus ready to go. And then, I guess that would be over here. And then the controller is gonna clock that data into the peripheral on that rising edge. So it has to be ready. And the thing that tells it to be ready is the chip select. All right. Ready for I2C? All right, see that time I got more head nodding. I think data got transferred to you guys. I appreciate the questions. Everybody benefited. Okay, we're talking about I2C, which is the integrated circuit protocol. Nobody has ever called it that, ever. I probably had to look it up when I made these slides. It's just I2C, I2C, that's what everybody calls it. Reading references if you get excited. This NXP manual is particularly good. It's just kind of nuts and bolts. How does this protocol work? Yep. So this is actually a fully defined spec. So it's developed by Philips in the 1980s for television sets so they could talk to the peripherals in their television set. It's the de facto today 2-wire standard, 2 wires for data and clock plus ground. And then eventually became a spec. So now every common peripheral, manufacturer makes peripherals that use I2C. In fact, because integrated circuit technology has gotten so robust, so we can get so many transistors on things for free, it's not uncommon to have a sensor or a memory module that has both I2C and SPI interfaces available. And usually there's like a pin, maybe you have to ground it or pull it up to VDD, and then that will tell what interface that chip will talk to, so to give you more flexibility. It also helps the chip manufacturers not have to make 2 variants of their piece of hardware. So that's a benefit from their supply line point of view. As you'll find out, is that this spec uses an address because there's only 2 wires, there's no arbitration line, there's an address, and it used to be, all this used to be licensed, and you have to license just to use this protocol. As of October 2006, there's no licensing fee required to use SPI, but they still have to register the addresses because you don't want 2 manufacturers using the same address and those having to collide and have issues on your bus. So there's a fee that's imposed to register the addresses, and that helps keep the ecosystem fairly reasonable. Okay, but this is a unique bus, and all that analog stuff that you wish I wouldn't talk about is going to come up. Here we have a controller, and you have, in this particular case, you have multiple peripherals. We'll show later that you could have multiple controllers on this bus structure. And they're connected with 2 wires. So one is serial data line, and here's serial clock line. And these are pull up. You have to use resistors to pull them up. It means there's open drain resistors or transistors in there. We'll talk about that in a minute. That's pulling the bus down, and then that resistor is pulling it back up. So these have unique addresses of 7, 10, or 16 bits. Again, look at your data sheet. You'll find out which one your peripheral requires. Address 0 is for broadcasting. It could be the case where you have multiple peripherals that kind of have the same protocol and you want to talk to them all at once. That's possible. You have to look at your data sheet. One of the challenges, as we'll see, is that speed is now not defined just by silicon. Speed, you want to go faster, well, those resistors are going to control how fast does that line get pulled back up. If it's a very large resistor meaning that it weakly pulls up current. Well, it can't pull that line up very fast. And so you actually get slower data lines. And if you want to go real fast, you're going to have a smaller resistor. The problem is now you have a trade-off between power consumption. Smaller resistors means higher power consumption and speed. So there's this trade-off here. It also means that you might be like in code telling it to go faster, and it just won't go faster. And now you'll forget that you actually have to go to your board and resolder something if you want those higher data speeds. But there's reasons for all this. And so here in this example, this is just the internal wiring here. We have, what do we have? A clock generator. So this clock is going to this MOSFET, so this is open drain. And then it's going to pull this line up and down. This one's going to receive that data, and if it wanted to, clock right now it's disabled, but it could talk back if it was set up as a master, but it's not. And data is bidirectional, so clock's not bidirectional, but data is. And so here we have data is being sent out here, pulling that line down, and this inverter is pulling that data into the data register. When it's this guy's turn to talk, he'll pull this line down, talk back and forth. The benefit here is now you could have two systems that are that have different voltages. So say this one was at 5 volts, and this one was at 3.3 volts. Well, as long as the VDD here, this pull-up resistor, both are tolerant to that, then they can talk to each other. So this is a way to have kind of voltage invariant buses. There's some details to keep track of. But it's also, there's another problem we'll talk about in a second, which is bus contention, which is solves more regularly. Yeah, and you can get multiple devices, so it's easy to get multiple devices, and you don't have to pay the penalty of the extra select wire. It's all about the addressing scheme. What questions do you have so far before I go into Falstad? Okay. Let's see. Okay, so here we have an example I2C controller and a target or a peripheral. You can see the current flowing. Those little dots help you visualize that current's going in or no current's going in. So this thing is creating square waves by remember this is just a switch that's either closed or open. It's either connected to ground or not. And when it's not connected to ground, then there's zero current flowing through that resistor, therefore V equals IR. The voltage on the other side of the resistor must be the same when no current's going through. So there's a mathematical way to understand why the resistor pulls things up. And then we have, on the top there, we have, this is a way to send data this way. So I'm going to go and push this, and you can see that data is going up and down over here. Okay. And you can see over here that this side changes. So when I go low here, it's low. I go high here. Ooh, come back. Okay. High, that goes high. Likewise, I can go high here. Wait a second. Why not happening? Oh, my fault. Reset. Why are these switches not switching? Okay. 70 millivolts. You're not being pulled high. This is peculiar. All right, well, let's go through this one. So I'll get back to the transmit side in a second, but this is a capacitor I switched onto the control line here, or the clock line. Now, nobody puts capacitance on your devices on purpose. This is parasitic capacitance, meaning unintended capacitance. Does anybody have an idea where parasitic capacitance comes from on your PCB or on your embedded system?
So like if you have a bunch of traces and they're parallel, they might generate capacitance? Like physics, maybe?
With physics, yes, fantastic, undeniable answer. Yes, that could be. You could have trace-to-trace capacitance. There's probably more typical ones. In fact, trace-to-trace coupling will cause interference where data going through this line will actually get coupled on the other line. That's probably the issue we care about more than capacitance. What's another mechanism for capacitance? Yeah.
Transistors.
Yeah, so like if we expand that idea out a little bit, your pin on your microcontroller and all the transistors that get connected to it will actually have capacitance there on the line. So you might test your device in isolation and you're like, oh, all the square waves are just nice, and you put a load on it, like a GPIO pin, and all of a sudden they start getting smoothed over. Also the geometry, maybe this is what you're saying a little bit, your traces over a ground plane or connected to other things will add some capacitance. And so, I don't know if you guys can see it, but this thing is kind of rounded over. So if we add this, make this larger, hey, why are you not working? Nothing's working. Okay, that did work. All right, so we can see as I increase the capacitance to pretty large, it actually is getting hard to get all the way up to the top. In fact, I could even make it super large. And see, oh, that was too super large. And so you can see this little thing is so large, we're not able to even pull that resistor all the way up. The resistor is not be able to pull the clock all the way up. And so now we have an issue where our clock speed is too fast for the hardware setup that we have here. That resistor is not able to pull the data up. So what would I do if I wanted to drive this clock correctly? What would I have to change about the circuit other than parasitic capacitance? Yeah.
You could reduce the resistance.
Yeah, let's do it. Now, you wouldn't want to do it this particular value. First of all, 10 microfarads of capacitance is a huge amount to have as parasitic capacitance, unrealistic. And you wouldn't put 100 ohms on this data line because it would consume too much power. But now you can start seeing that the clock is making it all the way back up to 5 volts. So now we made this trade-off between speed, how fast the bus can go, versus what our resistor values are. Yeah.
Why are there so many inverters? Are they just representing the different MOSFETs that are on the chip? You're like, why do we need 2 inverters on the I2C target in this?
You know, this is just a falsad construction. I just wanted to have the logical output line there, so this thing shows you the logic. And if I only put 1 inverter, so inverter is just a way to like turn the data, this kind of analog-y data that's going up and down, into ones or zeros, right, just for thresholding. And then I did it twice just to make sure the logic was in the right direction. I suppose falsed probably has a buffer somewhere in it that doesn't invert. I didn't find it.
Right. Thank you.
Yep. Now, I still haven't figured out why this thing is broken up here. Oh, there we go. It magically fixed itself. Maybe I made a small logical error somewhere. Let me turn off this thing here and put you back to 1K. All right, so if I change this thing, hey, there we go. You can see that this device has data over here. So I'm gonna clock that from 1 to 0. This changes over here, and this guy got the data, okay? Now I can change this guy. You can send data back. So bidirectional data on one trace. So now what makes this protocol horrible is you are with your little oscilloscope or your logic analyzer and you see traces going up and down. You're like, ah, it works. But maybe you don't know which way the data was going. Was it going from your peripheral to your target to your peripheral? And boy, it's just a good time. Just a good time trying to debug these things. What is the other problem here that could occur if 2 things are talking at once?
Collide and talk at the same time.
And then how will that manifest itself?
Like both of the signals would get.
Yeah, so the challenge would be if we had normal CMOS signals where you can drive the bus high or bus low, one could drive high, one could drive low, and then you'd burn something out, right? Because there's no resistance to ground. Here, one of the reasons they have the pull-up line is it's impossible to burn things out because you can both go, I can pull this low and I can pull this high as much as I want, but it's still low, right? But it didn't cause a problem. I'm still sinking this current. Here, let's increase the current simulation speed. I'm still dumping this current to ground, but I haven't blown anything up. One of the challenges is, let's bring that high. So they both have to be high. That's the resting state of the system. So if one controller here is just being a jerk and is holding this bus line down low, and this other thing, say it was a target, say you have multiple targets. Let's do it that way. You have multiple targets, and the controller wants to talk, and the target is saying, hey, I'm not going to release the bus. I can't pull it. There's no way to pull the line up. So that's the other reason to have this resistor, for bus contention, but it causes the problem that you can't get control of your bus back. What questions do you have? Yeah.
What's the need for having the capacitors? Like,
There's no need. It's a teaching example. So here, if I put this here, and I try to, all right, you have to be high, you're high, and you're high. And so I'm just trying to show you that this capacitance causes an issue. That's what I'm trying to show. In fact, if I take that away, like you saw before, it could be that you're going so fast that your RC charge up time is so slow that you actually miss data points, right? The capacitance is so high that it doesn't reach VDD over 2 to be counted as a logical 1. And then those cases, you either have to reduce your capacitance, probably impossible. You have to decrease your resistor value to drive more current, possible up to an extent, or slow down your bus.
So wouldn't you need some sort of extra lines to communicate when the target should be expecting input versus giving output?
No. But there's a protocol on top of this. We're just down at the signaling layer. But yes, there has to be some agreement of it's your turn to talk or my turn to talk. Yes. But we're going to do that a slightly different way. What other questions do we have? Okay. I encourage you to play with this. Really, the whole reason on homework 1 I made you deal with open drain, open gate, open drain circuits is because this is the time you use them in this class, and they're just an important concept. So remember, if you could think back to your GPIO pins, they actually give you open drain as an option. They also gave you resistors as an option, right? And why in the world were they doing that? Well, this is why, because they felt like, okay, STM can differentiate itself in the marketplace by not requiring vendors to use their chips to also put resistors on the bus, right? Now the resistors are part of the chip themselves, and you can reduce your part count and size and complexity. All right. Any other? Yeah.
If you're using that on-chip resistor, you have to be careful about how much. Could you potentially run into current limitations on your chip if it's having to pull up a really large line all the time?
Yeah. So is there state? Yes. So your resistor could be so large that it can't pull enough current fast enough for your given scenario. That's true. Typically, I worry about driving too much current through a GPIO pin and burning it out, like through a transistor or something. I worry about those things when I think about the error conditions where a device fails. Typically, most issues occur when you over voltage something.
So we're not gonna have to worry about the VDD we're feeding to our microcontroller. If we set all of our GPIO pins, for example, to be pull-up resistors, do we have to worry about it pulling too much current off that VDD or no?
No. I don't know, maybe. I think what will happen is there's a limit and it won't be able to, it would be more modeled so you're thinking there's, yeah, so you're saying this is a GPIO pin, right? Mm-hmm. And you're trying to, so you're gonna close the switch, so this is connected. And then what's the condition you're worried about?
Like if our GPIO pin is going out to some trace that has like really high capacitance or something.
Yep.
And has the potential to draw a lot of current when it's switching.
Yep.
Does that VDD from inside of our chip, is there like a current limitation of current coming into our GPIO pin through this resistor?
Yeah, there is. What would happen is this thing it'll act like there's more resistance up here. Like it won't, like there's all these other traces and stuff that will current limit it.
Or
And
like overheat the pin?
nah, you'll be fine. There's a very interesting edge condition. Well, we'll talk about that at a different point. But you can actually, I'll talk about it now because it's fun. Inside your devices, there are usually over voltage protection. So it usually looks like this. This is ground, and this is VDD. And so if this voltage goes above, like 0.3 volts above plus VDD, then it will start conducting current up into the VDD trace. And that's how we protect ourselves from over voltage. There was a project, and I found this air conditioner in a different way, where I put too high a voltage in here, and I actually started changing the VDD of the chip, which was still within spec, but the ring oscillator that I was using started changing its frequency because now the whole chip was at a different frequency. And so certain times when my little RFID tag was working, it would work fine, and then when I brought it close to the device, it would overcharge this pin, and then the clocking would get bad. So I had to learn a lot. All right, anyways. Any other questions, false static questions? All right, we'll get up to the protocol layer here. Nope. All right, so we talked about signaling, and now we'll talk about kind of timing diagrams. At the very beginning, there's a start condition. So this is where the controller will assert that it wants to talk on the bus. And first it waits to see that there's no traffic on the bus for a little while, and then it's going to pull the data line low. This is the start sequence. It's going to pull it low, and then it's going to start doing its clocking. That start sequence either tells, it depends on where you are in the protocol, either tells the peripheral, okay, get your data ready. If it's going to be talked to, we'll talk about that in a second, but it also just tells everything else in the bus, I'm taking control of the bus. Then you start clocking in data. Now this is a weird protocol where the clock edges happen, both edges happen inside the data. So before we talked about how there was a toggle phase or the setup phase, and then there was the clocking in edge. Here, both things occur. So here, you come in, you clock up and down inside the data edge. And so this is the condition in which data is clocked in. So there's no transitioning. The clock is not transitioning when the data transitions. So this is also kind of makes a little bit of sense if you think about that the clock has this RC discharge or charge up discharge cycle, and you have these little, in practicality, you have these little spikes that are coming up, and those are going to happen inside your data bits. So it also means that your peripheral or your device has to be a little bit more sophisticated in its timing, because it has to on its own know when to transition between the data edges. Ask me questions. I think I said it correctly. I think I transmitted information. Yes.
All good.
You spoke for the class. We're all good. Fantastic. We'll move forward. What am I? Okay, this is mostly about arbitration. This protocol allows you to have multiple masters or multiple controllers. And so the other controllers have to wait to see if the bus is clear, and then it tries to pull that line down. So if another controller comes in here and tries to pull that line down, it has to see that it's not available to it. In fact, it should try to release it to release control of the bus. So this is one of the weird protocols where you have multiple controllers talking at once. There's also a stop condition where data goes high, or clock goes high first, and then data goes high. So it's kind of the opposite of getting into it. Now, how most parts of this protocol work is that the arbitration method is addresses. So each device has burned in it an address. So at manufacturer time, that company worked with NXP to set, okay, this is the address for my device. And so the controller would say, okay, this address, and it would clock in address bits. And it says, okay, so here's the clock that's happening inside the data frame. And then it's going to say, I want you to be, this is a read-write request. Either I want to read data in, or I want you to write data back to me. And then there's an acknowledge bit. Now, the trick here is who's acknowledging in the acknowledging bit. So this is the controller sending out data. It's the target's job to acknowledge, which kind of blew my mind. Here's the address packet going through, and this part is controlled by the controller. This bit right here is controlled by the peripheral. And so one of the common mistakes happens is you're trying to write to some peripheral, and you're like, it always is knacking. Every time it knacks, knack meaning no acknowledgement, ack meaning acknowledgement, is always knacking. What is the error condition that can occur if you're always getting a knack? A knack is when this bit is high. Try to take 30 seconds, think about what happens if you're trying to keep talking to a device and you're never getting a response from it, and how that might manifest here.
If anyone pulls the load,
It's not properly.
that's what he meant by where it is. Because, I mean, he said it was start the peripherals pieces after. But you don't have to. There's the point of the clock or something. At least if you're waiting for you only have to release if you're looking for if you're waiting for an act.
All right, what do you think? It's kind of an open-ended question. Any ideas?
So my assumption is that the clock is fine, but maybe the packet is a different size than it needs to be.
It could be. So there could be an actual protocol reason, like, or that's not the address. I wrote this address, text something, and that device is not the address, it's going to knack. Now, the error condition that I was going for, but didn't set you up for any success in figuring it out, I realize, is that if there's no device actually connected to the board, this is going to be high. There's nothing to pull it down low, therefore you're going to get a knack. So it's not uncommon for a student to say, no matter what address I send to it, it always knacks. And you look at the horrible breadboard, and the wires are everywhere, and it just may not be connected, because a knack is the same as nothing. Nothing's happening. Okay? So you're looking for that knack. Says, okay, I acknowledge, the peripheral acknowledges that it got the data. So you got the address frame, and then you got the data frame. And so now you're going to put in 8 bits. It could be, there's different sizes that it could be, but here you put 8 bits, and it acknowledges that it got that data. Likewise, if this was a read, then you'd say read from this address. You pull the data out, and then it's the peripheral's job to respond. And so this is an example of a data frame here. This is multiple reads. So here's a write. So to this address, this data was written. To this address, data was read back. You can see that you can see the capacitance on the line here. We have this RC charge up. It's taking extra time for it to go up because those resistors aren't strong enough to pull it up very quickly. You can see the start and stop bits here for the protocol, where the data line is being pulled up before the clock is for the stop condition. And you can see the acks and knacks, and usually the end of the knack is I'm done with a transaction. That's usually why the last thing is a knack, when it's done. Yeah.
So the knack is to check for a hardware bug, something like that?
Knack is for the peripheral, or the thing that you're talking to acknowledge that it's gotten the data. So here, let's say the controller was writing in to address 100101110, it was nacked by being pulled low. So that means that the peripheral acknowledges I've got that data and I acknowledge that I have it in. Do you see the reason why we have ACKs now?
So like, if it like takes time to acknowledge, do they what if it's like after the
What conditions would you knack? Well, it could be that you try to write to an address that's not on the bus. You have 5 peripherals on the bus, you wrote an address that nobody's going to respond to, so nobody responded to it. And now the controller would know, oh, wait, that's not a viable option. So that's a reason for a knack. Or maybe the data got corrupted. That's a reason for a knack. How's that feel?
so it would just like write again to somewhere different?
Well, then what do you do if you don't get a knack? If you get a knack, what do you do? Well, that's up to you as a programmer to make that decision. You might say, oh, I've written this protocol that if the device doesn't respond, then I go talk to these other ones. I throw an error to, to the user. Who knows what happens? But then you'd have to make a decision what to do.
Can the peripheral drive the data line independently, or will it only do that when it receives a read instruction?
It needs a clock. The clock comes from the controller, so it's not asynchronous in the sense that it can decide whenever it wants to talk. It has to be, well, not asynchronous is the wrong word in this context. It can't independently decide I want to talk, so it always has to have the controller talking to it. So usually the controller gives it an address I want to read data out of, and then it will read data back. Does that make sense? Does that answer your question?
Some peripherals need more time to process that data. So do they pull like the SCL line like low until the slowest device is ready?
No. There could be, so say you give a command to a temperature sensor or a radio peripheral and it does take some amount of time. Well, you as the programmer have to know that beforehand. And you may know that it takes so long for this task to get done. So then you wouldn't come back. You might say, I write data to it. The data says, take your measurement. And then you have to know that you can't come back immediately with another address to try to read the data out because it's not ready. But that's not part of the protocol. So it's always the case where you can write and then, so you have address and then data. These can happen right after each other. There's nothing, the hardware should be able to respond quickly to that. It's just if there's an extra task, you might have to wait for that.
So the programmer kind of sets the time frames so that it matches the slowest.
Yeah, these are not high, this is not like Ethernet where all that timing, all that protocol stuff's baked in. You have to fully understand what the target's doing.
Is the packet of data that a peripheral would send based on a read instruction the same format with like a start and stop condition, 7 address bits?
Yes. Almost in all condition, the peripheral is not telling you what the address is. The peripheral, here what happened is the address came in and it's a read. So this particular you peripheral, I want to read from you. And then it's going to read data out.
What's the read-write bit?
The read-write bit is telling the peripheral, prepare to receive data or prepare to send me data.
What would it be when the peripheral sends it back?
It would be, I believe it's read, because it's from the controller's point of view. So I want to read from this address, and then it sends clocks out, and then data comes back.
So what's to stop the peripheral from reinterpreting its own signal as another instruction from the controller?
Well, that's a fine question. So there's an address. So there's a piece of logic in there. The address comes first. And so the controller is being like, when I get an address, then it's my job to do something else. And then it would send the data out. So it should be in the mode, if it's sending data out, it shouldn't also be expecting to receive data. Although I know in that fall stat, it gives the impression that data would come back in through but it's not precisely how it would work.
Is the ACK bit on the read transaction, the ACK bit in the data part of our read transaction, is that driven by our controller or by our peripheral?
Oh, so good question. So in this particular example, the controller has said, this address, I want to read from it. Data comes through, and NAC, the controller, is the thing that NACs, saying that I am done now. I've read the data. I don't need anything else. Yeah. All right, I had an exercise. I don't think we have time for it. Let's see. So yeah, to answer your question, the controller is done. It indicates a NAC. Why doesn't it indicate acknowledge? I don't know. It's buried in some person's brain who chose to write the spec in this particular way. That is just how it's done. Yes?
If we're writing, so like we send the write signal and then data is all zeros and we read from the same address, why wouldn't it read all zeros then?
All right, well, hold on. Say it again for me.
So like, maybe I'm just misinterpreting it, but like, I was thinking the first signal is like write to that address and it acknowledges it.
Yeah.
And then like the data that we write is all zeros.
Sure.
And then if we read from the same address,
yeah,
why wouldn't it like read out all zeros?
Ah, okay. That's a good question. So this is like this is just nuts and bolts, like talking back on a bus. But on top of that is what the chip does. So it could be that just, I don't know what all zeros means, go to register 0 and pull out data. So it could be like, here's the address of the device, and maybe this is the register in the device. I don't know. But like inside your data sheet will tell you how to interpret these bits and what should happen. But it's not defined by this protocol. It just is just a transport layer, not a MAC layer on top of what your devices do. Let's see. So how does does the peripheral know when? Should we know when to write data? So here's the write bit. The controller generates the clock for it to write data into. So the controller or the peripheral is not the thing that generates the clock. It's the controller. It's always the controller that's generating the clock. I know we covered most of these concepts already. Okay, so your I2C, your STM32 has 4 I2C modules. Now, you will read through the data sheet and see that some of these pins overlap with your SPI module. It's not like you could actually have 3 SPIs and 4 UART, 4 I2C, but there's up to 4 I2C. So maybe I'll ask you this. Take a minute or so, think about why is it that you'd want to have multiple I2C peripheral or modules on your device?
There's only one line.
So this is why we need multiple if you have legacy modules on the device. And I think
you could have put it in the address
I don't know. I just thought you were putting it
same address. If you pick 2 like edge sensors, so you need different buses. There's like a MAC
All right, what do you think? In the time we have remaining, why would you need multiple I2C modules on one microcontroller?
You have 2 devices that have the same address?
Yeah, this is a problem. You find some cool sensor, oh, you're like, oh, look at this distance sensor. It's really great. I would like to have 50 of them. Oh my God, that would be so great. I'll make a cool embedded system. But the manufacturer's only registered one address. Like, how do you get multiple devices when they only have the same address? And so this allows you to at least have 3. There are I2C address translators, so chips that you can put in between that will translate one address to another address, and that will allow you to have multiple of the same chip on a bus. But but it just becomes harder to use, yes. What's that? Can you have, 4, sorry. I don't know which I'm talking about, SPI or I2C. But yes, you can have up to 4. Again, there's a pinout problem that you're probably gonna have to sacrifice you're gonna have to sacrifice UART or one of the SPI buses to get that. But, yeah.
The reason why only I2C3 has the exon wake up from stop to mode.
Is there a reason why I2 has wake up on stop mode 2? I have no idea.